folks, I have gone back to a headset after trying a Bluetooth earbud kind of thing, which has a microphone in the wire, and it wasn't doing, very good sound quality. So I've gone and got another fancier headset, which looks very big, but I tested the sound. It sounds very good. So let's continue now with the related topic: modes and mechanisms of specific decadal scale variability. This is led by Manu Di Lorenzo and all the usual suspects of this field. So, again, this is a nice long paper, lots of information. Main things to remember are that there is evidence of decadal scale variability from the data. We don't have necessarily all the answers as to this selection of the time scale or the mechanisms, or whether they are intrinsically born in the extratropics or tropics, or there is an interaction. And when we say modes and mechanisms, we are talking about not just one mode but multiple modes. So it's a complicated story, but again, science works this way. You find data, you do some analysis, you find a hypothesis, you try to get more data to test the hypothesis before it can become a theory. And now, of course, we use models to see, can we do models. So here you have simple models, linear models, full models, stochastic models, statistical models, and so on and so forth. Again, I'm going to be brief and not go through all the details, because it's a really nice paper with lots of nice references that you have to follow up if you're interested in this topic. Okay, so Pacific decadal variability, Pacific Ocean, climate variability, climate change, ocean atmosphere teleconnections, El Nino, southern oscillation are all the key words of this review. This is also a review, annual review of marine sciences. What is the abstract? The modes of Pacific decadal variability, PDV, as opposed to TPDV that we talked about. These are traditionally defined as statistical patterns of variance, reflect to first order the ocean's integration, i.e. the reddening of the atmospheric forcing that arises from both a shift and a change in the strength of the climatological or time mean atmospheric circulation. So the idea is very simple. Atmosphere is very light, no heat capacity basically, and it has no memory, and hence it changes very fast in terms of winds and fluxes. And what does the ocean do with it? Ocean basically integrates it and produces lower and lower frequencies, because ocean has memory, high heat capacity, moves slowly, and so on. That's what this reddening of the spectrum means, that the atmosphere may be like a white noise, but the ocean takes it and produces frequencies which can be detected in the spectral analyses. Okay. While these patterns concisely describe PDV, they do not distinguish among the key dynamical processes driving the evolution of PDV anomalies, including atmospheric and oceanic teleconnections and coupled feedbacks with similar spatial structures that operate on different timescales. There may be El Nino, which is an interannual mode, and you may have a decadal mode that looks like El Nino, but timescale is very different. Okay, in this review, we synthesize past analysis using an empirical dynamical model constructed from monthly ocean surface anomalies drawn from several reanalysis products showing that PDV modes of variance result from two fundamental low-frequency dynamical eigenmodes. If you don't know what eigenmodes are, you have to follow up elsewhere. The North Pacific, Central Pacific, or NPCP, and the Kuroshio-Oishio extension modes. So North Pacific, Central Pacific mode, and a Kuroshio-Oishio extension mode. Okay, both eigenmodes highlight how two-way tropical extratropical teleconnections dynamics are both eigenmodes highlight how two-way tropical extratropical teleconnection dynamics are the primary mechanisms energizing and synchronizing the basin scale footprint of PDV. While the NPCP mode captures the interannual to decadal scale variability, the KOE mode is linked to basin scale expression of PDV on decadal to multi-decadal timescales, including contributions from the South Pacific from the other hemisphere. So it is a cross uh, equatorial interhemispheric mode, the KOE mode. Okay, and eigenmodes, in a simple way, there is some forcing happening, and there is, let's say, some normal mode that gets picked up no matter what the frequency. In this case, atmosphere may be just noise, but the coupled system with the ocean integrating is able to pick these modes as normal modes. So, what is the introduction? Traditionally, the low frequency variability of the climate system has been described in terms of modes of decadal variability, sometimes called oscillations due to their spatial seesaw like structure, such as the Pacific Decadal Oscillation, the North Pacific Gyre Oscillation, the South Pacific Decadal Oscillation, and the Interdecadal Pacific Oscillation. These are not necessarily independent, and depending on how you look, where you look, you end up with these modes. However, most of the named modes do not exhibit a preferred time scale of variability. Specifically, they are not periodic, since they are designed to capture statistical patterns that efficiently represent the strong low-frequency variance on interannual to multi-decadal timescales rather than low-frequency dynamical modes of the Pacific climate system. Lots of technical words, but just see if you can follow up with more reading from the references and so on, which are really a lot. So, very nice, rich text, but also very technical. Okay. Nevertheless, modulations of these patterns are linked to significant impacts on weather and extremes of the Americas and Asia, and to a large amplitude transitions in marine ecosystems, which is where the first decadal transition was noticed by the Japanese. I think they had a long time series of zooplankton and fish where they found these regime shifts, and then the climate people started to pick up on it and started to notice that there are climate modes associated with them. Recent examples of these modes impacting extremes include marine heat waves and droughts over North America in 2013 to 2015 and 2019, uh, and tropical storms. So there is lots of text that follows on how this paper is building on previous analysis that are being cited here. But I'll jump further to read the introduction to statistical patterns of decadal scale variability, which is where all the analysis started. Not like you discovered it in a model or that you suddenly found ways of representing it, but you kept finding them in data. Then people said that is just a statistical artifact, that it doesn't have a mechanism, and so on. But that some of that we read in the tropical Pacific decadal variability, where we said maybe there is a V prime T bar or a V bar T prime, or maybe it's just low frequency rectification of El Nino and La Nina. So it's similar here. Statistical patterns of Pacific decadal scale variability. The global decadal scale variability of sea surface temperatures anomalies shows that the tropical and North Pacific, together with the North Atlantic, are the most energetic regions of low frequency, which means 8-year low pass. So anything like El Nino is removed almost completely. So that's low frequency variability. Previous analysis of global SSTs have documented that several modes of PDV are main contributors to both global climate variability and fluctuations of the global warming trend, such as the 1998-2013 hiatus, which I have discussed elsewhere that you can look up. Essentially, there was a slowing down of global warming during this period, which is still debated. Some data claim that there was no slowdown, but I would say there is definitely evidence of a slowdown. These results are evident by decomposing the variance of the global 8-year low pass SSTAs into its first two empirical orthogonal functions. Again, you have to look up what they are if you don't understand. The first decadal global mode that we'll look at soon, explaining 34% of the total decadal variance, shows loading in the Pacific Basin that resembles the classical El Nino-like pattern of decadal variability, which was first reported by Zhang Battisti, Wallace, and so on. The second global mode is characterized by strong loading in both the Northeast Pacific and the Central Pacific, whereas the tropical Pacific decadal variability TPDV that we looked at is typically a maximum where? So where that is the Northeast Pacific and Central Pacific, that's where the TPDV is typically a maximum. Together, these two global modes capture the different flavors of Pacific decadal variability. This can be visualized and quantified by defining a PDV mode that is equal to the sum of the global mode 1 and global mode 2, i.e., a rotational rotation in the plane of the first two EOFs. That maximizes the variance, but essentially empirical orthogonal functions find the dominant patterns, and you can have n number of these EOF modes, which should add up to the total variance. So you're always trying to see what is the explained variance of the dominant mode and what is the spatial pattern, and there is a time series or the principal component associated with them, and you can superpose multiple modes to see what emerges. So here we are saying the sum of global mode 1 and 2 gives you the most dominant PDV mode. The resulting pattern that we look at is now dominated entirely by the Pacific Basin, and the temporal evolution of the PDV mode, that is the PC principal component, is strongly and significantly correlated with the interdecadal Pacific oscillation. Again, there is the word oscillation, and all other indices of the major named modes of Pacific climate variability. In fact, we can reconstruct each of the Pacific climate modes indices as a simple linear combination of the two global mode time series as a dot global mode 1 plus b dot global mode 2, as we will see, where the coefficients a and b represent the relative weighting of the two modes. So it's a superposition with weights, obviously all empirically derived. Okay, so we are basically explaining things using statistical approaches like EOFs, but then you have to go back and find the mechanism and make sure it's not just a statistical artifact, right? So if this is too technical, then don't worry about it. But if this is a topic of interest for you, let's say you're coming from the fisheries side and you're interested in the decadal variability and regime shifts, and then you have to worry about how global warming will modulate these modes, and whether these are purely natural modes, and so on and so forth, and how they interact with other low frequency mode across the planet, let's say in the Atlantic Ocean, etc. So lots of questions, but here just focus on Pacific decadal scale variability. Okay, here is a figure: EOF decomposition of global 8-year low-pass SST anomalies. Global mode 1 explains 34%, which has this structure that we looked at before with the Aleutian low, the Northeast and Central Pacific. We'll come back to Kuroshio-Oishio extension on this side, but it has this structure that we talked about before. Pacific mode 1 SSTA alone explains 40%. So there is, when you do global mode, you also capture the Atlantic. So pattern 1, Pacific basin scale with strong loading in the Kuroshio-Oishio extension. Okay, so second one, global mode 2 is 17%. You always have to make sure that they are independent. Empirical orthogonal functions by definition are orthogonal to each other, mode 1 and mode 2, but then you have to do rotation and so on to make sure that in fact they are completely independent. So Pacific SSTA alone would give you 17%, as so they are similar, but you can see that this looks somewhat similar with different loading in the south and weaker loadings on these sides. So pattern 2, Central Pacific and North Pacific. So you have to decide for yourself how convinced you are. So here the PDV mode is global mode 1 plus 2, which gives you this and increases the loading in the Pacific with interhemispheric patterns going all the way into the Southern Ocean. And the Atlantic multi-decadal oscillation mode is global mode 2 minus global mode 1, so produces hemispheric scale warming here, focused on the North Pacific, on the North Atlantic, but opposite sign here. But there are also signatures on this side. So all these are, there are lots of debates about the statistical significance and all, who's doing what, whether they are interacting with each other, they are independent of each other, whether the interaction is between tropics and extratropics, and so on and so forth, which I will skip. But reconstruction of the weighted sums, A dot global mode 1 plus B dot global mode 2 gives you the South Pacific decadal oscillation, and the IPO interdecadal Pacific Oscillation Index correlation is very high. SPDO index and the global reconstruction are highly correlated. Also for the IPO index, also for the PDO index, NPGO index, which will look at North Pacific Gyre Oscillation Index. The correlation is lower, but you can see it's still statistically significant and relatively high. TPDV again high, so even though we are doing these as two papers, you can see that they are closely related. So this is the decomposition of the global scale low frequency SSTA variance. The standard deviation of 8-year low pass NOAA SST product is decomposed into first two EOFs referred to as the global mode and global mode 1 and global mode 2 that we looked at here. So I won't read all the details, but you can see that together the first two global modes EOFs capture most of the spatial structures and temporal variability of the known modes of Pacific climate variability, such as the interdecadal Pacific Oscillation, Pacific Decadal Oscillation, South Pacific Decadal Oscillation, the North Pacific Gyre Oscillation, and the Tropical Pacific Decadal Variability. So we are not saying they are independent, we are saying there is a way to capture them. The second key figure, maybe this is getting a bit long, but I'll go a few more minutes. I'll definitely have to split this into two podcasts. The statistical patterns of PDV, which we will see here. It's a bit complicated, the figure, plus I have to run to another meeting. Panel A shows the mean atmospheric sea level pressure. Panels B and C show the first two dominant EOFs of sea level pressure anomalies in the North Pacific, tracking the Aleutian low and the North Pacific oscillation modes, respectively. And panel C and F show the respective oceanic expressions, the PDO and the NPGO, NPMM, North Pacific meridional mode, which we talked about before in the previous podcast. Similarly, panel D shows the dominant modes of the South Pacific sea level anomaly, tracking the South Pacific oscillation. Panel G shows its oceanic expression SPDO, and panel B shows its seasonal expression, the SPMM. So whenever you do this, you know that you are trying to see that low frequency is there, which means there is integration happening, because atmosphere alone cannot produce this. And then the question is, ocean expression has to be there, but is it coupled? Is it just the ocean integrating noise and producing this? But if you say there are impacts far away on the Americas and Asia, then you know that the signal is propagating in the atmosphere somehow. So there are modulations of the atmospheric noise, let's say, on low frequencies by the ocean manifestation of these modes. So the red and blue outline shapes in the atmospheric modes mark the locations of the mean SLP highs and lows, respectively. Rectangles in the mean circulation and oceanic modes represent areas where So let's just look at the figures. So mean circulation of the atmosphere, we have the Aleutian low, the North Pacific high, South Pacific high. The Southern Ocean is always different. So this is the North Pacific and South Pacific focus. So atmospheric modes, the Aleutian mode. So North Pacific SLPA mode 1, explaining 35%, captures the changes in the position and strength of the Aleutian low, which goes, north-south, expands east-west as well. So Aleutian low to PDO exists. So I chopped it off in different ways, but never mind. So North Pacific oscillation mode is the going from NPO, negative NPO to NPGO, and also to NPMM, the North Pacific Meridional Mode, which you can look up with John Chiang's paper and so on. So this is the North Pacific SLPA Mode 2 explaining 17%. This was 35%. So this captures changes in the strength of the mean atmospheric circulation of the North Pacific. So not just the Aleutian Low, but the entire North Pacific atmospheric circulation. So this is the January to March variability of the NPO here being one of the key factors. This is the NPO here. South Pacific Oscillation Mode, on the other hand, explains 40% of the EOF in the South Pacific SLPA. This captures the changes in the strength of the mean atmospheric circulation of the South Pacific. So South Pacific Oscillation to SPDO, the South Pacific Decadal Oscillation, and February to April variability of the South Pacific Meridional Mode. Meridional mode has extratropical to tropical connection of equatorial SSTs, tropical winds, and there are again theories of these things, which means we don't know the exact answer. So the ocean manifestations, North Pacific SSTA mode 1 explaining 23% that we called the PDO before. So you can see the amplitudes there. North Pacific gyre oscillation mode, which has this focus, it's the North Pacific SSTA mode 2 explaining 15%. Are they independent? Well, you can do rotation and so on to verify. South Pacific Decadal Oscillation Mode, 24% in the SSTA, South Pacific SSTA, so has a very strong El Nino-like signature here as opposed to the broader pattern here, but it has this strong South Pacific focus, of course. And South Pacific SSTA Mode 2 explains 14%, and it has this east-west pattern, which is somewhat like the ENSO transition mode that the Shikhar Srivastava, Arindam Chakravarti, and my paper explains. Okay, so we'll come back and look at Hasselmann's ideas in the next podcast, because this is already 22 minutes long. Essentially, that's the stochastic model that explained how noise from the atmosphere can be integrated by the ocean to produce low frequency climate modes, and he won the Nobel Prize, shared a Nobel Prize with Suki Managri and a physicist who did some kind of a symmetry work, if I'm not mistaken. But either way, climate scientists won as physics people in the Nobel category of physics. Okay, so I'll come back and continue, and maybe I should run to my other meetings. Okay.